1 second. Okay, so for the second talk of the day, we have Björn, who's going to tell us a little bit about F-theory uplift at large H11. Go ahead.
Yeah, thank you, Raj, Bruno, and to everyone else organizing the seminar series, giving me the chance to present this work in progress that I'm doing here in Madison with Jakob. But before we get into the physics, here's a quick disclaimer. This is me right now, but if you take this guy and evolve him back in time, you get this guy, but the last name has changed. So if you're wondering about the last names, these two people are actually the same up to symmetry transformation. So if you ask either of these guys, what do people do in string pheno, or what can people do? Either of these guys would come up with a list of this form. So if you want to make progress in string pheno, you can try to use the generic predictions of string theory and derive the consequences, whatever it is. But it's of course very challenging because we don't know so much about the string landscape. And in fact, we don't even know how much we know about the string landscape. So of course, you can then turn to achieve a better fundamental understanding of string theory and try to understand more of the landscape. For example, you study string scattering amplitudes and derive whatever you can do from there. Or you can try to take whatever you have and make the best models you can do, like the most precise, most advanced models you can make. And this approach is then useful to prove existence statements about the landscape, to show that certain features do exist in the landscape. But of course, it also leads to a better understanding of the landscape itself. Of course, you can also, if you want, study what is not possible in string theory along the lines of the swampland. So for the sake of this talk, I picked bullet point 3 that I want to do. So we're trying to make models as precise as we can, study some existence statements, and also understand the landscape better using this approach. And the corner of the string landscape we understand the best is probably type 2B compactifications on Calabi-Yau manifolds. And if you want to go to n equals 1 supersymmetry, we have to go to Calabi-Yau orientifolds. So we study type 2B string theory, pick a Calabi-Yau by 3, orientifold it such that there are O3 and O7 planes. We can put flux on it and arrive at a 4D n equals 1 supergravity theory, where the data of the supergravity theory is derived from the Calabi-Yau geometry and the branes that live in this space. What you can then do is to uplift all this stuff to F-theory, where you basically trade some branes, the 7 branes, for geometry. So you no longer have a Calabi-Yau orientifold and branes living on it, but you just have a high-dimensional Calabi-Yau of 4 folds, and the branes are geometrized. If you do that, you can achieve understanding of non-perturbative effects in type 2B string compactifications. But you can also study the perturbative regime of type 2B. But now you have more geometric methods available to do more detailed computations. And this is kind of the approach I want to take today. And if we want to make this very precise, we have to construct these Calabi-Yau manifolds, their orientifolds, and their uplifts to F-theory in a precise way. And the best tool we have available these days is to construct these Calabi-Yaus as submanifolds in toric varieties. So a toric variety is basically a fancy way of saying it's a complex manifold that is very similar to C star to the D. So a D-dimensional toric variety is just C star, the complex plane with the origin taken out. And then at higher codimensions, some interesting things happen. Here's an example of the probably most simple toric variety, which is P1. And you can view P1 as a C star most of the time. So you can decompose C star into the radial direction and the circle direction. And you can view P1 in this way, where it's a circle vibration over the interval. And if you are somewhere in the interior of the interval, you have a perfect circle over the line. And then over special points, the endpoints of the interval, the circle shrinks to 0 size, and thus makes a sphere as a circle vibration over P1 with 2 special points. And toric varieties basically means taking this concept and generalize it to all possible ways, to higher dimensions, of course. And it has proven that toric varieties allow us to systematically construct a huge variety of complex manifolds. And this is, of course, what we need if you want to study Calabi-Yaus because Calabi-Yaus are complex manifolds. So toric varieties generalize this concept of you have C star to the D and then some special points. And the way you do it, or the way you can formalize it nicely, is that you start with a lattice that is always called N, and this kind of stands for this C star to the D. So we have a D-dimensional lattice if you want to base a D-dimensional toric variety. And then this boundary data, the special points where things can happen, are encoded in so-called cones. And the cone is defined as a positive linear combination of lattice generators. So basically what you have to tell us to specify for a complex toric variety is we have to tell you how does the C star to the D behave at certain points and how do these cycles degenerate. Everything is collected in the data of cones, and if you collect the cones together, you get what is called a fan, and the fan just tells you how do these cycle degenerates over various loci to form an interesting manifold. These fans are usually represented in this way. So we have our lattice N, and we have some lattice generators that are parts of our fan, and the cones are then combinations of these lattice generators. And how this works, here is a quick example. We go back to P1, which is a one-dimensional complex variety. So we are in a one-dimensional lattice. And the fan of P1 has two cones, two one cones, the red one here and the green one here. And the way you should read this fan data is as follows. There's always a trivial cone, which is just the origin. And this always corresponds to C star to the D. In our case, it's just C star. And then every cone adds some piece of interesting data to it. One cones add points at codimension 1, which is just single points because we're in one dimension. So each one cone here adds 1 point to C star. And we know if you add 1 point to C star, you get C. If you add another one, you get the famous compactification to a sphere. And this is P1. So the most important cones in any dimension are just the one cones, so the lattice generators that make the fan. And these are called the rays. And these are important because you can associate to every ray of the fan a coordinate. And these act like homogeneous coordinates, just as the homogeneous coordinates of P1. And in this case, we see we have two rays. So we have two homogeneous coordinates. And these are precisely the well-known homogeneous coordinates of P1. Furthermore, to every coordinate, we can also associate a divisor by setting this coordinate to 0. Of course, if this restricts to a codimension 1 subspace, which is a divisor, and everybody calls these divisors D sub I. And these are the most important objects in toric varieties. So now that we have a rough understanding of what a toric variety is, let us construct a Calabi-Yau. So the problem is that there's a theorem that compact toric varieties can never be Calabi-Yau. So what you have to do is you have to construct these Calabi-Yaus as submanifolds in these toric varieties. And the simplest thing you can do is construct at codimension 1, so as a hypersurface in a toric variety. And the way you do that is you use the general theory of toric varieties again, that tells you that the most general divisor you can write down, you can always write it down as a sum over these divisors di that you simply get by setting one of the coordinates to 0. There's another theorem that tells you that if you want to get a Calabi-Yau hypersurface, you have to set all the coefficients here to 1. Okay, that's a theorem. Furthermore, what you can do is understand this corresponding hypersurface, this divisor here, as in terms of a hypersurface equation. So you can write down an equation, a polynomial equation, in our homogeneous coordinates xi, and setting this to 0 gives us the submanifold that we are after. There's a systematic way how you understand how many monomials contribute to the polynomial and what the coefficients are in each of these monomials. Each monomial comes with a parameter, and these parameters parameterize the family of Calabi-Yaus, the complex structure moduli of our Calabi-Yau. However, we are not after constructing Calabi-Yaus only. We want to construct Calabi-Yau orientifolds and then uplift them to F theory. And a simple way to construct Calabi-Yau orientifolds is to first construct an obifold of our toric variety, and then study what happens to the subvariety that is the Calabi-Yau. The Calabi-Yau orbifolds that are involutions, so that generate a Z2 orbifold, are studied in the past, and it turns out that they are generated by lattice vectors that are half integer, or in other words, by vectors that lie in this lattice. So they are kind of half the size of a usual lattice generator. There are different choices of these lattice generators, and different choices due to different forms of orbifolds and to different forms of orientifolds of the Calabi-Yau. So when you start out with the fan that looks something like this, then you add this generator to your lattice. So your lattice becomes more fine. That's what it's called, the lattice refinement. And then you have to take your fan, adjust it in a certain way such that your orbifolded variety is as smooth as possible. That means sometimes you have to shorten your lattice generator. Sometimes you have to add new ones so your fan can look a bit different after you do that. But there is a systematic way of doing this to construct a toric variety orbifold V-twiddle with an associated fan sigma twiddle. And of course, you can also study that effect on the Calabi-Yaus. So if you have constructed a Calabi-Yau in a toric variety, now you orbifold the variety, you can understand how the Calabi-Yau orientifold looks like that you construct in this variety. So we had our polynomial f that cuts out our Calabi-Yau, and the systematic way to get to the orientifold is you project this f on the orientifold covariant monomials, so the ones that are like even or odd onto your orientifold involution. And you want to project on the right ones such that, in our case, the Calabi-Yau orientifold has O3 and O7 planes. You can do that, and from this data, you can derive a new hypersurface in our orbifolded variety that we can again represent by the sum over these divisors that you get by setting a homogeneous coordinate to 0. If you have this form available, you can again translate this to a hypersurface equation. This will again be a polynomial in our new homogeneous coordinates x twiddle of our orbifold. And we can study this Calabi-Yau orientifold just as before. There will be polynomials, monomials, polynomial deformations, and so on. In some cases, this hypersurface can be a toric variety itself, because this is no longer Calabi-Yau. So the theorem that toric varieties can never be Calabi-Yau doesn't apply here because it's not a Calabi-Yau. Calabi-Yau orientifolds can be represented as toric varieties itself, sometimes. In general, they are not, but sometimes they can be. So if we now have such a Calabi-Yau orientifold at hand, we want to uplift this to F-theory. And F-theory means the following thing. This should represent this drawing, the base here should represent our Calabi-Yau orientifold. And then you add a torus vibration over our base space. And this torus vibration degenerates over certain points, precisely those points where the seven-branes sit. And the way how one constructs such a torus vibration is again by a hypersurface. The best way to do that is to define this space, that's some weighted projective space, P231, and then define an equation, the Weierstrass equation, in that space. And if we now want to fiber our torus over our base, we first have to fiber this P231 over our base and then impose this equation. This is how it is usually done. In the Weierstrass form, you present an F-theory model in the Weierstrass form. But however, in our case, if you want to do this most precisely, and we don't have available that this Y3 can be represented as a toric variety, but itself is a hypersurface, we have to do the following thing. We have to construct a toric sixfold, which is given by a 2-3-1 vibration over our orbifolded toric fourfold, and then impose two equations on our toric sixfold that cuts out the Calabi-Yau fourfold. One is the one that cuts out the elliptic fiber of the P231 space, and the other one is the one that cuts out our Calabi-Yau orientifold from our orbifold fourfold. So what we construct is, first we have our toric variety, we orbifold it, then we do the P231 vibration over it and impose two equations now. These two equations can again be represented as some divisor classes that can, of course, be expanded in terms of our favorite divisors d sub I, setting a homogeneous coordinate to 0. And of course, we can then also go from these divisor classes to polynomials that, when you set them to 0, you get our hypersurfaces. Now there's a problem. If you do that, in general, what you will get will be a singular manifold. This will especially be true at large H11. So if you have many Kähler moduli of your Calabi-Yau, then it's generically the case that this is a singular manifold. That is not necessarily a problem to the F theory in the first place, but if you want to get a systematic understanding of your manifold, maybe compute certain quantities, having a singular manifold is problematic. Also, it doesn't capture the entire physics in this case, because there is some physics hidden in these singularities. So what we want to do is we want to resolve these singularities. So what are these singularities like? Let me go again on the left. This is again our favorite picture of a torus fibered over our base that can degenerate at certain points. If it degenerates at a certain point, that doesn't necessarily mean that our manifold is singular. If there's a seven-brane in the theory, it doesn't mean the total manifold is singular. However, if this degeneration is severe enough, think about putting more seven-branes on top of each other, then the entire thing becomes singular. Oftentimes, what you can do is, well, if you put seven-branes on top of each other and this makes it singular, why don't you pull them just apart and resolve the singularities? Well, sometimes you can do that. This is what I tried to depict on the top right. If this thing is too singular at this point, you can pull the seven-branes apart, trade one bad singularity against two that we can actually understand, and this manifold is smooth, and we can do all our operations in this that we want. But sometimes this deformation, which is a complex structure deformation, is not available to us. There are simply no moduli of the manifold that allows us to take the seven-branes apart. However, there's a different thing we can do. It means in the gauge theory language, this means going to the Coulomb branch. And in the geometry language, that means that we resolve the singularity not by removing apart the seven-branes, but remove apart the singularity in the fiber. In other words, we do a Kähler resolution. So we move along the Kähler moduli space, and we blow up a divisor that is of P1 type in the fiber, and then a divisor in the base. And this can always be done, but the question is, how do we do it in practice if we are given our Calabi-Yau in this codimension 2 form in a toric variety? So first of all, our equation, the Weierstrass equation that cuts out our elliptic fiber, is always of this form, where F and G are sections of appropriate line bundles on the base. And if we are given this form, we can identify the loci where these singularities appear by finding those homogeneous coordinates where the generic section of these line bundles already takes this form. Oh, the 2 shouldn't be here, excuse me. So there will be an overall factor of xi total squared and xi total cubed for F and G. And that means that this surface here is our singular surface, and we cannot deform it away. This is what is called a non-Higgsable cluster. And in our case, the associated singularity will always be of D4 type, because this is the only type of singularity that can occur in a weakly coupled type to B regime. And what we want to do is we want to do a Kähler resolution where we want to blow up divisors such that in the fiber we get P1s that intersect according to the Dünken diagram of D4. This is what Kodaira famously told us can be done if we have a D4 singularity available. And our question is, how can we do this systematically given our construction of our singular Calabi-Yau in the codimension 2 complete intersection model? And here's the answer. So we know that the singular locus in toric variety language is contained inside the cone that is spanned by the rays associated to x and y of our P231 vibration and our x twiddle I, the locus where the degeneration occurs. And what we found is that you can resolve this space by blowing up 2 points in this space. So now you might ask, why 2? Didn't I tell you we need 4 blow-up moduli to resolve this? And the answer is that it will be two blower moduli in the Calabi-Yau sixfold, but one of them descends to three moduli in actually the Calabi-Yau. Oh, sorry, did I say Calabi-Yau sixfold? I meant toric sixfold. And then one of them descends to three moduli in the Calabi-Yau fourfold. We can find for each such non-Higgsable cluster the rays that we have to add, which correspond to the blower moduli explicitly. So we add two rays to our toric fan, and then we have to subdivide the fans. That means we have to define the cone structure accordingly. And it turns out that this E1 ray that we add corresponds to three devices in the Calabi-Yau. And you can see that if you go to the local picture in the Weierstrass model, you can see that the Weierstrass model takes this form. And you can see if you set E1 to 0, we'll have a cubic equation in x and x twiddle. And this means that on the Calabi-Yau, this has three solutions. So that means that this divisor on the Calabi-Yau splits up into three divisor classes. And these assemble precisely in the way, thank you. These assemble precisely in the way to form this D4 Dünken diagram. And we can do this systematically, so we can resolve systematically all these singularities. Once we have that available, we can study what the properties are of the manifold we constructed. So just to recall, we started with a toric fourfold and a Calabi-Yau inside of it. We did the orientifold, so we have now an orbifolded toric fourfold and a Calabi-Yau orientifold inside of it. Then we constructed this elliptic vibration on top of it to get a sixfold, toric sixfold, and a Calabi-Yau fourfold with singularities inside of it. And then we were able to smoothen out all the singularities to get a smooth Calabi-Yau fourfold in this toric sixfold. We can do all of this in a systematic way. In the regime we are working in, we can also from here identify which moduli correspond to the seven branes and which correspond to the bulk. So we can gain a geometric understanding of the moduli space. We can, of course, study not just one such model, but the software developed by the Cornell Group, CY Tools, allows us to construct many models and analyze many models at the same time. And all these models have this feature that the uplift is not favorable. This is the thing I just explained before, that the Kähler moduli of the Calabi-Yau fourfold are not all inherited from the Calabi-Yau sixfold, from the toric sixfold, but some of them, are special moduli. However, the complex structure moduli space in all models we have studied so far can be understood in a favorable way. So now there's one more thing left that would be nice to have for these kinds of models, and this is to compute superpotentials in F-theory thereon. So we started out with our type 2b model, and the superpotential of this type 2b model can be computed in F-theory by the F-theory superpotential in this way, which basically means that we have to be able to compute the periods of the Calabi-Yau fourfold. There is a way to systematically compute such periods in the large complex structure limit if the mirror manifold of our uplifted Y4 is known. So if you want to do precise computations, we not only need to understand what the Y4 is, we also need to understand its mirror. And this can be challenging, but there are tools available how we can understand the mirror. For hypersurfaces, so for Calabi-Yau hypersurfaces, this was famously done in like 93 or so. And the result is, if our toric fan derives from a so-called reflexive polytope, that means all the rays in our fan are points in a polytope that has like this algebraic feature, then we can understand mirror symmetry in a rather easy way. But now we don't have a Calabi-Yau hypersurface, we have a codimension 2 Calabi-Yau on a toric sixfold. So the question is, how does this generalize to such situations? And the answer is it does generalize, but it gets a bit more complicated. What you have to do is you have to construct, again, a polytope, which is basically just to take the convex hull over all rays in our fan. And this has to be reflexive. But this is just one condition. Furthermore, there's a second condition on our two divisor classes, that you have to be able to partition them into like two sets, such that our coefficients that define our divisor classes fulfill these properties. And if you have that available, we can understand mirror symmetry again in like a combinatorial way, similar to this, in the following form. Instead of having two polytopes that are reflexive, one is reflexive to each other, we now have to have two polytopes on each side of the duality. Because we have two equations, we can associate two polytopes to each of these equations. And from two polytopes, we can make either we take the convex hull over both of them, or we sum them together. And this makes two polytopes on each side of our duality. And all of these polytopes have to be reflexive, and they have to be reflexive pairs towards each other. And if this situation is given, then we can understand mirror symmetry in a combinatorial way. We have a good chance of computing the periods, and we have a good chance of understanding what's actually going on in our type 2b description. For example, if you have this situation available, you can understand the Hodge numbers in a combinatorial way, similar to the hypersurface reflexive case. And for all tests we have done so far, these Hodge numbers came out precisely on the norm. So let me summarize to get to the end. What we have done is we found a systematic way to go from Calabi-Yaus to Calabi-Yau orientifolds to the uplifts F theory. And these can be efficiently studied using the software CV2, for example. This allows us now to study F theory models in great detail, especially in the situation when mirror symmetry can be understood. And in these cases, one can then get a good understanding of the seven-brane moduli, and then one can attack problems such as the seven-brane moduli stabilization problem. And this is, of course, to be done in the future. And here I just say thank you, and I'm open for questions.
Thanks a lot, Björn, for the talk. Do we have questions for Björn? Sab, go ahead.
Hi, Björn. Thank you for the for the nice talk. Have you looked at the Euler characteristics of the spaces that you can build this way? Like there was some record large Euler characteristic from the fourfold built from Candelas and friends, I think a long time ago.
Oh,
Do you think you can get something?
We have not yet looked at like the extreme cases, but this is certainly a thing we should do, yes.
Yeah, do you have a sense that you might get something bigger potentially, or you think that might stand?
You mean by going
like
to like the complete intersections rather than hypersurfaces, there can be some larger?
Yeah.
I cannot exclude it. But of course, there are special types of fourfolds that allow for a weakly covered type 2b regime. So that also gets rid of some fourfold models. I don't know. It would kind of be surprising to me, but I cannot rule it out. But this is something we will certainly check in the next few days, weeks.
Great, thank you.
Any other questions for Björn? So maybe I can ask you something quick. Maybe you mentioned it. So here when you say study properties of the F theory uplift in more detail, are some properties kind of more obviously related to what you're doing? Like are some specific things about the F theory uplift that becomes much clearer with this kind of formalism, or it's more generic? You just are able to study more cases.
So we are able to study more cases. To my knowledge so far, these cases with these non-Higgsable clusters, they are hard to treat in an analytic way because you have to do these blowups and so on. So now you can do them systematically. That's a big plus. And these cases appear most of the, I mean, this is the generic feature, especially at large H11. So if you want to study, for example, if you wanted to study the F theory moduli stabilization, seven-brane moduli stabilization problem, you of course want to start with situations where there are a few seven-brane moduli. That means few complex structure moduli in your Calabi-Yau fourfold. But this means you will have a lot of Kähler moduli in your fourfold. And these are precisely the models that were previously very difficult to understand in F-theory.
Hmm.
So especially for this modular stabilization problem, having this formalism available is very important.
I see. Okay, thank you. If there's any other question, we still have a few seconds left. So take your chance now. Otherwise, if there's nothing urgent, we can thank Bjorn for his nice talk.